All right, let's continue on with this video. So going through the second half of this exam, this is where things start getting a little bit trickier. So question 5 here off the bat, we have this question here that relates to what appears to be a hyperbolic function that has this rule here. Always a good idea with these questions that involve calculus, just off the bat, before we even start answering it. Just write it with negative indices. Get rid of that thing down the bottom. Right? So this is going to be equal to 3,000 times t plus 1 to the power of negative 1. That helps me, at least. It might not help you. We know that this function here models the population of a town after t years. We want to use this function to predict the population of the town after 4 years. So to do that, we just need to go ahead and make a substitution. So we let t equal 4. We get that the function is equal to 3,000 times 4 plus 1 is equal to 3,000 divided by 5, which, okay, 3,000 divided by 5, we should think, okay, what's 30 divided by 5? 30 divided by 5 is 6, so therefore 3,000 divided by 5 is going to be equal to 600. That was a 0.95 average, so 95% of people got this one here correct. And really this question is just assessing, can you divide 3,000 by 5? So if you're pretty comfortable with your division skills, this question should not be an issue to you, hopefully. Okay, moving on to the next question here. So yeah, we've got a new function now, h1, models a population. We know that h1 when t equals 0 is equal to h when t equals 0. We also know that h1 decreases at half the rate of h at any point in time, or in other words, we should say that the derivative of h1 is equal to half the derivative of h. So let's work out what the derivative of h is. We know that h is equal to this thing here, 3,000 times that. So the derivative of h is going to be equal to 3,000. Well, what we would need to do here is we need to decrease this power. So it's going to go from t to the power, so t plus 1 to the power of negative 1 to t plus 1 to the power of negative 2. And we need to multiply by the current power. So this is going to come out as 3,000 divided by t plus 1 squared, right? So that's our derivative here. So because h1t is equal to half of h, so the derivative of h1t is equal to half the derivative of h. The derivative of h1 is going to be equal to negative 1,500 times t plus 1 squared. Okay, and then we need to use that to work out what is h equal to. So now we need to take the integral of that to go backwards, and the integral of this is just going to be 1,500 divided by just t plus 1, so we've gotten rid of that square term there. Let's neaten that up a little bit. So 1,500 over t plus 1 plus c. Just taking the integral of that, we produce this result. Okay, next thing we need to use is this initial condition that we've been given, which tells us that, so that's the h1 function. We know, well, let's just write it out. So we know that h0 is equal to h10. So what do we know about h0? So h0 is simply going to be equal to 3,000 over 1. So that's 3,000 over 0 plus 1. So that's 3,000. That's going to be equal to 15,000 over 1 plus c. So in other words, 3,000 is equal to 1,500 plus c, or in other words, c is equal to 1,500, all right? So therefore, we can work out that the formula for h1t is simply going to be equal to 1,500 over t plus 1 plus 1,500. And the question's asking us to state a sequence of two transformations that produce this. So our first transformation to go from H to H1 is going to be a dilation factor. So we're going from 3,000 to 1,500. So that's a dilation factor by a half. So H is dilated by a factor of a half from the t-axis or parallel to the h-axis. That's what or you can say like in the h direction, they're all valid. And after that's happened, this is followed by a translation 1,500 units in the positive h direction. We could also say up as well here, but the positive h direction is more accurate. Okay, so that's how we do this. And this question here actually had an average of 0.3 marks, and only 2% got this question fully correct. So if you're not too good with your transformations, this could be a little opportunity for you, but also you're in good company. A lot of people did not get this question right last year, so that is how you do it. All right, next question. We've got confidence intervals. All right, confidence intervals. What are those again? Well, they're written over here on the formula sheet. There's how we do it. So the method is, or the formula is, it is the sample proportion plus or minus z's times, this here is actually the standard deviation, or sigma. So that's our range here. Okay, so first up, what are each of these things? So, okay, first up, we're told z is equal to 2. Okay, z is equal to 2 right off the bat. So we know that in a town, 100 people are randomly selected, with 60 people indicating that they're unhappy with their roads. Well, that's just the sample proportion, so p hat. P hat is equal to 60 out of 100 people are considered successful, so we're saying in this case, success is that the person is unhappy with the roads, strangely enough. So that's 6 out of 10 or 3 out of 5 is our sample proportion in this particular case. Our n value is equal to 100, and yeah, z is equal to 2. So that should be everything that we need in order to answer this question. So what we need to work out now, to use this formula over here, this one, we need to know what our standard deviation is. So standard deviation for a sampler proportion is equal to p times 1 minus p over n. Once again, I found that here on the formula sheet. So let's go ahead and do that. By the way, it's p hat here, so a sample proportion. That is going to be equal to the square root of 3 over 5 times 2 over 5, that's the probability of failure, which ironically is, I guess, the people are happy with the roads, and we're dividing that by 100. So that's going to come out as the square root of, okay, so 3 times 2 is equal to 6, and then we've got 25, and then we're going to divide that by 100. So that's 25 times 100 in the denominator over here. So going over here, that's going to come out as the square root of 6 up the top, and then down the bottom here we've got 5 times 10, which is square root of 6 over 50 is our standard deviation in this particular question. So that's the standard deviation of the sample proportions here. And now all we have to do is go ahead and substitute it into we're going to substitute it into this formula, which is p hat plus or minus z times the standard deviation of p hat to get our confidence interval. So let's work out that confidence interval. Our lower bound is going to be this here. So p hat is 3 over 5 plus or minus 2 times standard deviation is root 6 over 50. That's what we've worked out. So yeah, let's start with the negative case here, and then we're going to have the positive case, so 2 plus root 6 over 50. Okay, so can we simplify that down at all? You betcha we can. So that's going to be equal to 3 over 5 Okay, 2 times 50 is equal to, sorry, 2 divided by 50, that comes out as 1 over 25. So that's negative 6 over 25 to 3 over 5 plus root 6 over 25. Okay, and we could actually simplify that down further, but I think that should be good enough. I think we've just written it like that. That's our confidence interval. It's only worth 2 marks anyway, so that is 1.2 was the average mark here for this particular question. So once again, most people are getting some marks here. They probably found part of this at least. They drew out some of the correct formulas. So yeah, and just good to note here, z is equal to 2 is not completely accurate here. It's a good approximation for these tech-free assessments. What we've basically worked out here is 95%. We know this roughly, it's not a real rule, it's sort of an approximate rule, but we know that roughly 95% of data in a normal standard, a normal distribution is going to be within plus or minus 2 standard deviations of the mean. Right, so this little interval here, the area under that curve is approximately equal to 95%, but in actual fact, the real z-score is actually closer to 1.96. So this is fine for the tech-free questions in exam 1, but in exam 2, we'd have to be using inverse normal CDF to work out more accurate z-scores. But like I said, this is fine for this tech-free assessments that we're looking at right now. Okay, so next question. We're after new context. A new sample of n people results in the exact same sample proportion. Okay, so what does that mean? Well, we're told now that the exact same sample proportion has arisen. So I guess let's call this sample proportion 2. Sample proportion 1 was 3 over 5. So sample proportion 2 is also 3 over 5. Makes things easy for us. We want to find the smallest value of n to achieve a standard deviation of root 2 over 50. Standard deviation. So that's this formula here. Once again, it's the same one. That is standard deviation of sample proportion 2. Got too many hats. So that's sigma of p hat 2 is equal to root 2 over 50, and that's equal to this sample proportion, so 3 over 5 times 2 over 5 over n, and we don't know what n is, okay? So we're trying to figure out what is the n that gives us this answer. All right, so simplifying this down again, we have the square root of 3 times 2, so that's 6 over 25 over n. Okay, so we can deal with that. So that's just going to be the square root of 6 over 5 times the square root of n. We can simplify that down like so. So we've now got that root 2 over 50 is equal to root 6, which is root 2 times root 3, over, so times 5 root n. Okay, now on both sides of this, I'm seeing root 2's, I'm seeing 5's, so let's go ahead and simplify this a little bit. That's just equal to 1 over 10. 1 over 10 is equal to root 3 over root n. Let's square both sides now to get rid of those square roots. So that's 1 over 100 is equal to 3 over n. And yeah, now we can just multiply through here. So cross multiply, we're going to get that n is equal to 300. That is our the smallest possible value of n that could result in this particular standard deviation. I'm not sure. Yeah, I guess, yeah, this is the minimum. It could be, this could have been a larger fraction that gets simplified down to this, but yeah, so 300 is the answer to this particular problem. And the average mark for this was 0.3 for this question. So a lot of people not getting this one right. Only about 30% of people got that one right, but it definitely gets harder than that. So we've got this next question here, which is absolutely insane, this question, the amount of skills that it assesses. So we've got this little logarithm equation, which doesn't look so bad on the surface. So let's just go ahead and do it. Whenever we've got a logarithm equation, we want to go ahead and make all of the logarithms written with the same base. So we're going to see if we can do this. So first up, let's use our log laws. We know that this log is going to be equal to, well, we've got this number at the front here. We can actually bring that into the logarithm as a power. We can then write this as log 3x, and we could also write the number 2 as 2 times log 3 of 3, which of course we can then write as log 3 of 3 squared. Okay, or log 3 of 9. All right, now also on the left-hand side of this equation, we have log plus a log, so we can use our log law that says if we've got a log plus a log, we can just multiply those two things inside the brackets. So we have log 3 times x minus 4 squared times x is equal to 3 squared, which we said is log 3 of 9. And I've got two things on both sides of the equal sign here that have a log 3 in front of them. So if log 3 of something is equal to log 3 of something else, those two things in the brackets, you better believe they are the same thing. So let's now write that out. We have x minus 4 squared times x is equal to 9. Okay, so now we can expand the brackets. So first up, this square here is x squared minus 8x plus 16. X is equal to 9. Then we can expand this fully and then minus 9 from both sides. So this is x cubed minus 8x squared plus 16x minus 9 is equal to 0. All right, so that was our first step, I suppose. Okay, second step, we need to try and figure out how the hell are we going to factorize this. So the first thing that we need to do, let's suppose we call that p of x. We want to find, using the factor theorem, what is a factor. So we're going to first try a factor of 1. So remember, we're considering what are the factors of -9 here. So one factor, 1 would be a great option. It's usually going to be 1 or -2. So let's see if we get this right. This gives us 1 cubed minus 8 times 1 squared plus 16 times 1 minus 9. That's equal to 1 minus 8 plus 16 minus 9. And that does come out as being equal to 0, which is fantastic. We got it on the first try. So yeah, that's 1 plus 16, that's 17, minus 8 minus 9, that is equal to minus 17. All right, so 1 is a factor. So let's write that down. 1 is a factor, just so it's really clear what I'm doing here. So we found a factor. We can now use synthetic division to factorize this and write it as a linear factor times a quadratic factor. So let's do that. So what we do for our synthetic division method is we put the factor outside of this little shape here, and then we write in the coefficients of each of these numbers in descending order. So it's 1, -8, 16, -9. That's our cubic. We then drop that 1 down straight away, and we go 1 times 1, which is equal to 1, -8 plus 1, which is equal to -7, 1 times -7, which is equal to 7, 16 plus -7, which is equal to +9. 1 times +9 is equal to 9, and then -9 plus 9 is equal to 0. We know that we did this correctly because we have a remainder of 0 at the end there, so there's nothing annoying happening here. And that just tells us that px, so this polynomial, this cubic that we found here, is just equal to x squared minus 7x plus 9. So that's these three numbers down here are our coefficients. And then we have the linear factor, which is x minus 1, right? Because if x is equal to 1 gives us 0, then x minus 1 must be the linear factor. All right, now what can we do with that? Well, guess what? Now we have to actually complete a square because we've got a quadratic here. In order to factorize that quadratic, we need to think, what are the two numbers that add to give -7 and multiply to give 9? Well, guess what? There aren't any. So we're going to have to complete the square. Okay, so let's do that. Um, and this question is insane in the amount of content that it manages to assess. So let's go ahead and do that. So they've really crammed in these 4 marks. So px is equal to, let's just leave the x minus 1 out the front here. To complete the square, we write the first and the second term, so x squared minus 7x. We then plus 7 onto squared, so half the coefficient of x squared minus that number, and then we have the plus 9 at the end there. And that subtraction just makes sure that these two things are the same as one another. Okay, so let's now complete that. So we have completed the square. We can now factorize the resulting perfect square here, which is x minus 7 over 2 squared. We can then simplify this bit down the end here. So that is 49 over 4. I want to write 9 as a denominator of 4, so that's equal to 36 over 4 is the fraction there. And then don't forget there's large brackets around the outside here. That's x minus 1. And then over here, well, okay, so let's simplify this down. Firstly, we've got x minus 7 over 2 squared minus, okay, 49, so negative 49 plus 36, that is equal to 13. So that's 13 over 4. And of course, we could write that as a, sorry, not like that. We can write that as a difference of 2 squares. Because we could say that this is the square root of 13 over 4. Squared is the same as 13 over 4 because the square and the square cancel each other out. So that then just allows us to write this as a difference of 2 squares, x minus 1 times x minus 7 over 2, and then we're going to have the plus case, so plus 13 over 2 because the square root of 4 is equal to 2, and then we have 3 minus 7 over 2 minus square root of 13 over 2. All right, and we are trying to figure out when is all of that equal to 0? Okay, and it's all equal to 0 when x equals 1, when x equals 7 over 2 minus root 3 over 2, and when x is equal to 7 over 2 plus root 13 over 2. Is that the answer? Well, no, it is not, because we now need to consider the domain of the function. So let's go back to our original thing. We've got logarithms here. So whenever we're dealing with logarithms, you're really, really careful. So the thing is that each of these, like the domain of a logarithm, is strictly positive. So that means that, for example, x needs to be greater than 0, and also x minus 4 needs to be greater than 0. And that's the stronger case that we need to consider. X minus 4 is greater than 0. So let's go through all of these. Well, first up, if x equals 1, then what do we get? Oh, why is that doing that? Please go away. There we go. Can you not? What is going on? Okay. X minus 1. If x equals 1, then of course we have negative 3, which is actually less than 0. So we can rule out x equals 1 as a valid solution. What about if x equals 7 over 2 minus root 13 over 2? Well, then we have that 7 over 2 minus root 13 over 2 minus 4. Well, what's that? So that's going to be minus 8 over 2. So that's going to be, yeah, that's going to be a negative number as well. So that's less than 0. Unfortunately. And then what about if x is equal to 7 over 2 plus root 13 over 2? Well, then we're going to get 7 over 2 plus root 13 over 2 minus 4. So that's going to be equal to root 13 over 2 minus, minus, that's 8 over 2, so that's minus 1/2. And of course, root 13 is quite clearly, that's larger than a half. So that is in fact larger than 0. So therefore, x equals 7 over 2 plus root 13 over 2 is the only solution, and that's worth 4 marks. And I don't know about you, but I think that takes up an awful lot of space. So if you can do that a little bit faster, that would be amazing. I mean, I was explaining it as I went through that, but gee, that question, it's amazing how many areas from functions and relations and algebra that they've managed to cram into that one. That was an average mark of 1.4 marks, and only 9% out of the cohort who sat this test got this question fully correct. So, yeah, pretty tricky question, that one. Okay, let's move on and look at the next one. Okay, so we've now got a what's the word? A composite function. So we've got a product of two functions here. We've got this function f of x is equal to x sine x, and the first question is a trapezium rule question. So we've got this thing here. It looks like it's got a maximum somewhere up here. It's not completely clear where that maximum is. We'll get to that later. But yeah, so we've got this trapezium rule. We're told that the trapeziums are going to have a step size of a pi on 3. So that's going to be our first trapezium. That's going to be our second trapezium. That's going to be our third trapezium here. Okay, so remember, the area of a trapezium, right? Area of trapezium is equal to a plus b over 2 times, that's it. A plus b over 2 times h, where the trapezium looks like this. That's our h, that's our a, that's our b. This is our little trapezium here. So we need to find each of those areas. So let us, that's right. A plus b divided by 2 times h. Okay, so we've got this factor of a half then. So the area of this overall thing is going to be equal to a half times h, which we're told is pi on 3. And then for each of these 3 trapeziums, we need to add up the 2 endpoints. So it's going to be f with an input of 0 plus f with an input of pi on 3. That's going to be the first trapezium, plus f with an input of pi on 3, plus f with an input of 2 pi on 3. That's our second trapezium. And then f 2 pi on 3 plus f pi. Okay, so we need to know what all of these things are here. So let's just quickly work that out. So all right, so let's consider each of these. F0 is 0 times sine 0. And sine 0 is just equal to 0. So f0 is equal to 0. You can see this looking at the graph. You can also see looking at the graph, pi. So pi times sine of pi. Well, if we think about the unit circle, right, we're over here, pi, sine is the y-coordinate, so sine pi is also equal to 0. So we've got those 2 endpoints. They're nice and easy. Then for pi on 3, that is going to be equal to, so f pi on 3, that's going to be equal to pi on 3 times sine pi on 3. Now, sine pi on 3, this is where we need to reach for our special right triangles. So this is the one that's like an equilateral triangle of side lengths 2. And we've taken that triangle, we've split it in half, we've got this, and this angle right here is our pi on 3 angle. So if we have a look at that pi on 3 angle, the sine of that is going to be equal to root 3 over 2. So this is pi on 3 times root 3 on 2, which we can write as root 3 times pi over 6. Finally, we have to consider what is f of 2 pi over 3. So that's going to be 2 pi on 3 times sine of 2 pi on 3. So sine of 2 pi on 3. So where's that? 2 pi on 3. Well, that's going to be the second quadrant of the unit circle, so over here, and sine's also positive in that region. So that's just going to be the same thing. So that's also going to be root 3 over 2. So all up, this is just going to come out as, 2 pi on 3 times root 3 on 2. The 2's cancel out, and that's just going to be equal to root 3 pi over 3 is our answer here. All right, and now we just need to take all of those things and substitute them into this expression. So that's going to give us pi on 6. Okay, so going through each of these, this first one is 0. This second one is root 3 pi on 6. We've got 2 of those, so we times that by 2, plus the next one is root 3 pi on 3, and again, we've got 2 of those. So let's simplify that down. We've got pi on 6 times, got 2 of these guys over here. So that is going to be, so 2, that's just going to be root 3 on 3 pi, plus 2 root 3 pi over 3. So all up we have 3 root 3 pi's over 3. So the 3's are going to cancel out there, and we're just going to be left with pi on 6 times by root 3 pi. And that just comes out as root 3 pi squared over 6 is our area. So a lot of weird algebra there, but I guess this is further into the exam, so this is where the questions should be getting pretty tricky. The average mark there was 1.4 marks. So once again, a lot of people getting part of that, but it looks like that that kind of algebra towards the end there, or that kind of simplification there. Why is this doing this to me? There we go. That simplification there really screws people over. So make sure you know how to do sort of simplifying with pies and with fractions, because really tricky question there. All right, next question is actually nice and easy though. There's nothing too hidden to this one. So getting back to it, we've got this as our function here. The question's just what's the derivative of that? So we'll go ahead and write it back down for you. So we've got f of x is equal to x sine x, and the derivative of that, f of x, so f dash x, we're just going to use the product rule just like we did last time. That's going to be equal to, okay, so first up, take the derivative of x, that's equal to 1. 1 times sine x, that's just sine x. Next up, we're going to leave that as x and take the derivative of sine x. So that's going to be cosine. So we have x times cosine x. This question here, 0.8 was the average mark, 80% success rate. Most people are getting this question right. So that question should not be too much of a trouble for you guys. The next question here, again, maybe it's slightly harder. So the first thing that you should note here is we're asking about this range of the interval. So this interval for the function. So it might be a good idea to go back to the original graph and just consider that range. So we're interested in the range from pi on 2 to 2 pi on 3. So that's this range here. What we notice about that is that the function is strictly increasing over that range. So why is that useful? The fact that f of x is strictly increasing? Well, it just means that in order to figure out the range of this function, we should just need to consider the 2 endpoints, and then that's going to give us an idea for the range of these values, to figure out the maximum value and to figure out the minimum value of this particular function. So we've got the f dash x is equal to we've got f dash x is equal to what was it again? Sine x plus x cosine x. We're going to go ahead and sub in endpoints. So the 2 endpoints here are x equals pi on 2. So that gives us sine pi on 2 plus pi on 2 cosine pi on 2. So sine pi on 2 is equal to 1. And cosine pi on 2 is equal to 0. So that's just equal to 1 all up. Then let us consider the other endpoint, which is 2 pi on 3. Okay, so sine of 2 pi on 3 plus 2 pi on 3 times cosine 2 pi on 3. Okay, so first up, sine 2 pi on 3. We had that one before. That was equal to positive root 3 on 2. And then we've got this cos 2 pi on 3, which is just going to be equal to negative a half. That one should be. So that is going to be negative 2 pi on 3 times negative a half. Yeah, so that's where this negative sign here came from. Okay, so that's root 3 on 2. So yeah, the 2's cancel out. And yeah, root 3 on 2 minus pi on 3 should be the endpoint there. So yeah, therefore we can conclude that the range of this particular function is just going to be from root 3 on 2 minus pi on 3 up to 1. And we're including those endpoints there because we included the endpoints of the domain. So we've included the endpoints of the domain, so we'll also include the endpoints of the range. Okay, so now we're going to hence, by the way, that question there, it was only a 0.2. Only an average mark of 0.2 for that question, so a lot of people struggling with that one. Okay, so hence verify that f(x) has a stationary point within this domain. So what are we checking here? So what this means is, okay, so if we've got here these two values, if we have this, so the two endpoints of this range, if one of them's positive and one of them's negative, then that means that somewhere in between those 2 points, there must be a point where the value is equal to 0, where the output of this function is equal to 0. So the question that we're asking here is, what we need to check is root 3 on 2 minus pi on 3, is that less than 0? Because if it is, then we know that 1's positive. If it is, then we've got a value on one side that's 0, one side that's positive, one side that's negative. 0 must be somewhere in the middle. This is one of those rules that we looked at somewhere early on in the textbook. So let's just go ahead and do that. I'm just going to rearrange this slightly. So we can just add pi on 3 to both sides of this inequality. We have root 3 on 2. I'll leave it blank. So something, say question mark, pi on 3. Okay. And yeah, so we can then cross multiply that. So cross multiply like this. This gives us that 3 times root 3 is equal to 2 times pi. That is correct. Yeah, okay. So looking at these two things, we know that, well, we know that 3 is less than pi. Right, so pi is 3.14159.265, etc. And 3 is definitely less than that. And also, the square root of 3 is less than 2, because 2 is equal to the square root of 4. Right? So therefore, putting these two things together, it must be the case. So this was a question mark, it's not equal. It must be the case that 3 times root 3 must be less than 2 times pi. And if that's true, then it is also true. Therefore, root 3 on 2 minus pi on 3, that must be that must be less than 0. So, thus, we can conclude that the sign is going to be, so the sign at pi on 2 is less than 0. So this is greater than 0 when x is equal to pi over 2. And at the other endpoint, 2 pi on 3, we have that the output is less than 0. So there must, thus, I guess we should write this better. So thus, as one endpoint is greater than 0 and the other endpoint is less than 0, the derivatives of these two things, there must exist x somewhere between those two things. So pi on 2, 2 pi on 3. There must exist an x between those 2 points such that the derivative f dash x is equal to 0. Okay. So that question there, that was only an average mark of 0.1 marks. 0.1, yeah, so 10% of students getting that question right. Not particularly great, but that's kind of how you can go about getting that question. All right, so moving on to the next question here. So on the set of axes below, we need to sketch the graph of the derivative function over this domain. We're also going to use the fact that there's a local minimum for f dash x. So this is confusing, right? There's f dash x and there's f of x. So the derivative, we're sketching the derivative function here. And we're going to use the fact that the derivative has a local minimum at these 2 points. So a local minimum and a local maximum. So before we do that, let's just consider these points. So this is the maximum here. So the maximum occurs. It's not actually exactly at 2. It's at 2 pi over 3. So we found that before. Is it 2 pi over 3? Anyway, we've got the maximum here. Yeah, it should be about 2 pi over 3. So it's like there somewhere. So that's our maximum value here. Sorry, no, it's the value when the derivative is equal to 0. So the derivative is equal to 0. We don't actually know where the derivative is 0, but it's going to be somewhere here. It looks like it's somewhere here. So that's our first endpoint. That's our second point when the derivative is 0. And you can also see that the derivative is 0 when x is equal to 0. When x equals 0, derivative 0, that should be pretty non-controversial here. So we can go ahead and label the local maximum, which occurs at 1.1, 1.4. So that's going to be somewhere around there. So let's go ahead and label that 1.1, 1.4. And we're also going to label our minimum, which is at negative 1.2. So negative 1.1, negative 1.4. Those are the points of interest. We're also interested in the endpoints once again. So just be careful when you're drawing these things to label those endpoints. So the endpoints here, the domain is negative pi to positive pi. So substituting those into our function, input of pi is going to give us sine pi plus pi times cosine pi. Okay, so sine pi, that is 0. Yep, because sine is the y coordinate. And this is, so cosine pi is actually negative 1. So that is 0 minus pi, which is negative pi. And then f with an input of negative pi, the other endpoint, that's sine negative pi plus pi cosine negative pi. So once again, sine negative pi is 0. And cosine of negative pi, that is going to be, sorry, this is a negative sign here as well, isn't it? So it's cosine, yeah, with an input of negative 1, negative pi. So that's actually negative pi times negative 1. So double negative, that gives us positive pi there. So our two endpoints are pi negative pi, which we can chuck in over here. It's going to be somewhere about there. So that is the coordinates pi negative pi. And our other endpoint is negative pi. and positive pi, which is somewhere there. So negative pi, positive pi are our two endpoints. And now all we have to do is just sort of connect all of those points as smoothly as possible. This looks terrible, but hopefully you can kind of see everything that matters here. Don't forget the solid dots for the endpoints there and the endpoint there. So that's our curve. And just draw it a little bit more smoothly than how I've drawn it here. We should label the origin here as 0, 0. I don't think we know what these other x-intercepts are. Oh no, we've actually been given them. Yeah, so we are told, in fact, that the oh no, we don't know what they are. I don't think we can figure out those other x-intercepts are in this particular graph. But yeah, that's all you need for this one. Here you needed to label your endpoints. Yeah, so label the endpoints with their coordinates. That's the most important thing to label here. And the rest of it, you just need to make sure that your shape looks good. And yeah, like you've used solid dots for the endpoints to indicate that it is including them. So the average mark, like I've written here, is 1.1 marks. So yeah, again, not a lot of people getting all of the marks here. So that's kind of the process that you can go through to sketch the graph of the derivative. All right, moving on to the very last question, guys. So this question here, question 8, we're looking now at something that involves a bunch of letters. So yeah, we'll just go ahead and have a look at it. So we've got this function here. G is this cubic thing, or it's a square, a cube root function, where k and m are both real numbers. And we're told that p is a point on the y-intercept. So it's the y-intercept of the graph y equals x squared, sorry, y equals gx. And we need to find the coordinates of p in terms of k and m. So going ahead and doing that, we're just going to go ahead and substitute in 0, because when we're dealing with y-intercepts, we have x equals 0. So that's going to give us 3 times the cube root of 3 minus k plus m. And the thing about cube roots is we can actually just take that negative sign outside of that. So that's going to be negative cube root of k plus m. And yeah, that's basically all we need to do. So therefore, p has the coordinates 0, negative cube roots. Let's make it clear. So the negative sign's here, right? This is a negative number, not a negative root. There's no such thing as a negative root. So negative cube root of 3. Maybe it's best if I write this with powers. So that would be negative k to the power of a third plus m. So we could write cube root as power of a third. Plus m. All right. So that question there, 0.6 was the average mark. So 60% of students got that one right. Should not be one that you're struggling with. Okay, next question. Find the gradient of g at p in terms of k. So we're interested in the gradient of g. So straight away, we should be taking that derivative. Let's just write this function here slightly differently. We could say that this is equal to 3 x minus k to the power of a third plus m. So if I'm taking the derivative of that, I need to take the derivative of that thing there. So I'm going to take out the 1/3. I'm going to decrease the power by 1. So it's going to make the power to the power of negative 2 on 3. And then, of course, the derivative of m with respect to x is 0, because m's just a constant, so that goes. So tidying that up, well, we can't really tidy that up. That's the derivative. Okay, cool. So we've got that. Now we want to find the gradient of g at p. So at p, x equals 0. So we need to substitute an x equals 0 into this. So we have a third times 0 minus k, negative 2/3. So yeah, we can tidy that one up. So that is going to be the same as 1/3 times negative k. Now the thing is here, just be you can be confused about this, right? It's like power of -2/3. What does that mean exactly? Well, that's squares and then take the cube root of that thing. So when we have -k squares, that's just going to be the same as k squared, because when we square a number, if it's negative, it becomes positive. So this is just equal to a third times a squared. And then we could take the cube root of that. So we could just write that as k to the power of 2/3 is just a slightly nicer way of writing this. Or sorry, k to the power of, that's still a negative there. So we could write it like that. We could also write it with the square root. So I'll write it with the square root. So it could be written as, for example, 3 to the power of the cube root of k squared. And yeah, you want to write these things, your final answer, with positive indices. VCAA will not accept the negative indice answer. So either leave your final answer looking like this, or you could write it as 3 to the power of 1/3 times k to the power of positive 2/3. You don't want to leave any negative indices in your final answer. And the final one here, this had an average mark of 0.8, which is about 80% of students getting this particular question correct. Okay, 2 more questions to go. We're so close to the end. Okay, so now let's see this question here. We've been given that the graph of y equals x squared y equals gx passes to the origin. We need to express k in terms of m. So if it passes through the origin, right? We know it passes through 0, 0, just finishing the thought there. So therefore, g of 0, that must be equal to 0, right? So g of 0, that's this function here. We've already got that from before. In fact, it's right here. So so g of 0 is this thing. Oh, sorry, that was the derivative. That's why I'm confused. Yeah, so that's up here. So we've got this cube root here, which we worked out is this. So negative k to the power of a half plus m, that's equal to 0. So if that is equal to 0, then we can plus k to the power of a third to both sides. We can find that m is equal to the cube root of k, which is the same as k to the power of a third. If I cube both sides here, we can find that k is equal to m to the power of 3. And that's the answer. That's all we have to do here, right? So if k is equal to m to the power of 3, that's the answer. We've expressed k in terms of m. That question had a 50% average mark, so about most people getting this one right. All right. The last question, pretty tricky, is where we sort of combine all of these different elements. The question is, we're going to say that let point Q be a point that is different from the point P, such that the gradient of Q at points P and Q are equal. Given that the graph of y equals gx passes through the origin, find the coordinates of Q in terms of m. Okay, so the gradient of g at these 2 points is the same as one another. So that means that the gradient when x equals 0, which is this point P, remember, so it's a bit confusing, but at point P, that's when x equals 0, that is going to be the same as this other point. So at 0, we have this thing here. We have 3 times k to the power of 2/3. That's from part B up here. We can then take that, because we want to know the coordinates of Q in terms of m. So we want to get rid of this k. So to do that, we can just go ahead and substitute in k is equal to m cubed. So that's m cubed to the power of 2/3. The 3's are going to cancel out there, which is quite nice. So we get 1/3 times m squared is our gradient of the function g at x equals 0. So what we want to find here, we want to find x such that g dash x is equal to g dash 0. So therefore, we're going to consider when does this constant, 1 over 3m squared, that needs to be equal to the gradient function, which we found back in part B just here. So that is 1/3 times x minus k. I'm not going to write k, I'm going to write m cubed to the power of -2 over 3. I'm just getting that from just here in part B. Okay, so looking at both sides of this, first thing that we can see is that there's a third on both sides. We can get rid of that. That's going to come out as 1 over m squared is equal to x minus m cubed to the power of -2 over 3. Okay, what can we do about that? Well, let's just square both sides to get rid of, square root both sides. Is that what we want to do here? Yeah, so we could just write this 1 over m to the power of 2. That's just the same as m to the power of -2. So yeah, we can just square root both sides, or I guess just raise both sides to the power of a half, or I guess -1/2, and then that just means that x minus m cubed to the power of a third is equal to just m. So that just makes our life easier. And then we can just cube both sides here. So this gives us that x minus m cubed is equal to m cubed. So I've just gone that to the power of 3 and then this one to the power of 3. And then I'm going to plus m cubed to both sides. And then we can find that x is equal to 2m cubed. Awesome. Okay, we're almost there. So now we've got the coordinate, we've got the x coordinate of this point, rather. We want the overall coordinates of Q. So we now need to substitute x equals 2m cubed into the g function, into y equals gx. So let's do that. So in other words, what is g of 2m cubed? So that is going to be equal to, going back up here, it's that guy there. So that is, we've got the cube root of 2m cubed minus m. Just remember, k was equal to m cubed from before. And then we've got a plus m over on the end there. So tidying that up really quickly, we have the cube root of m cubed, because 2m cubed minus 1m cubed, that's just equal to 1m cubed, plus m. And of course, the cube root of a cube, those two things cancel each other out. We just have m plus m, that is equal to 2m. So therefore, coordinates of Q are 2m cubed, 2m. And that is the final answer there to that question. That last question there, by the way, that was an average mark of 0.5, and only 9% of students got that one fully correct. So pretty tricky question to end the exam on there. All right, so that is that's exam 1. We've gone through the entire thing now. Going over that, there's quite a lot of questions of a range of difficulties there. Really quite a tough exam. And of course, you can expect that this year's exam will probably be a similar level of difficulty, right? So we should be focusing on what? We should be focusing on our algebra skills. We should be focusing on being able to use our formula sheet accurately, and we should be focusing on being able to simplify things. So knowing how to do things like rationalizing denominators, simplifying fractions, doing quadratics, so expanding, factorizing, all of those skills are really crucial. Being really careful with double negatives in questions like this one over here. So loads to unpack with that particular exam. All right, so I'll create another another video like this for exam 2 at some stage soon. But until then, have a good one, and I will see you guys in class. Catch you later.